So hello everyone and welcome to the next ANITA lecture. Just to remind you, ANITA is the Australian National Institute for Theoretical Astrophysics, and we're a chapter of the Astronomical Society of Australia, and we represent theorists and observers who are interested in theory in Australia and even internationally. The next ANITA lecture we have for you today will be given by Paul Lasky from the University of Melbourne, who will be talking about gravitational wave astronomy. We hope this will be interesting. Just to note that we're trialing a new Q&A, so hopefully you may be able to see in the sidebar a place where you can submit questions to Paul, and he'll see those and answer them as he's speaking. So please participate. It'd be great to get your questions and have you involved. If that's not working for you, I'll be watching the Google Plus page where this is being posted, and you can just leave your questions in the comments there, and I'll pass them on to Paul as we're going along. Anyway, without further ado, thank you for watching, and I'll hand it over to you, Paul. Thank you.
Okay, great. Thanks, Darren. And thanks, everyone, for coming along. So what I want to tell you about today is this exciting field of gravitational wave astronomy. And I say it's exciting because I think the next sort of 2 to 3 to even 5 years is really going to be quite revolutionary in what happens within this field. So hopefully you can all see my slides. What I have on the first slide there is 3 images. The one on the top left is an image of one of the LIGO interferometers. The image in the bottom left is what space-based gravitational wave astronomy is going to look like in the reasonably distant future. And apparently the slides are dark. This is an issue. Sorry all. I'm just okay. In principle, that should have worked, but no. Still having an issue. Sorry, all this seems to be disastrous. Okay, I'm going to have to switch computer. Very sorry about this. Please don't drop off the line. It's going to be an amazing talk. It's going to be so fantastic. So while I try and sort this out, how is that now? Hopefully people can have downloaded the slides. I'm not sure if that's actually a... you can download the slides from... Darren has set up a link on the website. Okay, so I have no feedback on whether you've got that or not in your screen. So I'm just going to continue assuming that it is. And again, I apologize sincerely for this. So if Darren could please, yep, that's good. Okay. All right. Let's start afresh. Sorry about that. So if we move on, I'm going to go to slide 2 now and move along quickly. I do apologize. So one of the reasons that this field is so exciting, as I mentioned, is that there's going to be Advanced LIGO, the Pulsar Timing Arrays, which I think I forgot to mention in my introduction. Pulsar Timing Arrays are very are basically doing astrophysics now, and hopefully we'll have detections in the very near future. So what I've got up on the screen now, at the top of the screen, is a quote from the GWIC roadmap. Now, GWIC is the Gravitational Wave International Committee, and they sort of did like a decadal plan in a sense. They created a roadmap in 2009, and the punchline from this roadmap was what's written on the screen there. So in the next decade, the field of gravitational wave astronomy should become an important component of the worldwide astronomy effort, especially if real integration and synergy with other branches of astronomy can be achieved. So this is what I really wanted to get across with this talk today, is that gravitational wave physics is no longer just, in the near future, is no longer just going to be a pure physics experiment. This is really reaching into the branches of astronomy, and it's going to be reaching into the branches of astronomy in the very, very, very near future, in the next couple of years. So as you can see on that slide, I've got a whole bunch of images of various telescopes around, well, these are actually mostly around Australia. So SkyMapper, MWA, ASCAP, the ZADCO telescope and the AAO are all Australian telescopes that have signed memoranda of understanding with LIGO and are going to be doing follow-up searches for gravitational wave events. So the idea is that you get gravitational wave signal and you trigger one of these telescopes, or you trigger all of these telescopes to try and do follow-up. So in this talk I want to get across that, well, one, as I mentioned, that this is something that's going to happen very soon, and also, two, that this is going to influence many, many branches of astronomy. So the other three instruments that I have there is HESS, which is sort of high-energy gamma rays, SWIFT, which is gamma ray and X-ray, and IceCube, which is also a neutrino detector. And these as well are instruments that are currently being used to do a follow-up to LIGO. So if we move on to slide 3, I've just got a brief outline of my talk. I want to give first a very brief introduction to what are gravitational waves. So this is going to definitely be non-exhaustive, but I have provided some links to some more exhaustive texts. And then I want to jump into two different sections. The first is detecting gravitational waves on Earth. So this is using ground-based interferometry, which is the main experiment is LIGO, and I should put in a disclaimer here that I work on LIGO and I'm a member of LIGO. So I'm going to talk about how LIGO works. I'm going to talk about the sources and the event rate predictions. And I also want to focus a little bit, spend a couple of slides on what Australia is contributing to LIGO as well. We're then going to move on and talk about the Parkes Pulsar Timing Array and Pulsar Timing Arrays in general. So I want to talk about how exactly they work, and then do some astrophysics, talk about some of the astrophysics with the Pulsar Timing Arrays and where that is up to at the moment. Below the line there, I've got detecting gravitational waves in space using ELISA. This is something that I probably won't get time to go through, but I've created some slides for people to have a look at, and we can talk about it if we find there's time. Okay, so moving on to slide 4, what I've done with this talk is I've basically introduced key concepts that I want to get across. So, you know, this section is basically what are gravitational waves, and the key concepts that I want hopefully everyone to walk away from is that these are a direct prediction of Einstein's general relativity. And the other thing is that we've actually indirectly observed them already. So we have great confidence that these things exist, that we know the magnitude of them, or the actual amplitude of the gravitational waves, and they're as predicted. So if we move on to slide 5, the sort of first piece of evidence that gravitational waves exist won a Nobel Prize in 1993. So hopefully many people will know about this famous Hulse-Taylor binary pulsar. The basic idea here is that there's a binary neutron star system, and the orbit of this binary neutron star system is decreasing at a rate of around about 3 millimeters every 8 hours. And basically what you can see, the plot on the right, is quite a famous plot where data has been collected from around about 1973 all the way to 2000, and in fact this plot goes on a lot further into 2014. The vertical axis is the change in period, where 0 is obviously the period of the initial period, and the blue points are the data, and the black line is actually the prediction. So the black line is not actually a fit, but this is a prediction of Einstein's relativity that says, okay, we expect so much gravitational wave energy to be emitted from this system. This predicts a decrease in the orbital period, and this is exactly what you expect. And so you can tell that those match up perfectly, and as I mentioned, in 1993, this was awarded a Nobel Prize. So this is excellent evidence that gravitational waves exist, and they have the properties, at least some of the properties that we expect them to, and that are predicted by Einstein's general relativity. Okay, there's been a couple of recent papers on other binary systems, and of course David Parkinson gave a great talk on this ANITA online lecture series a while ago about the BICEP 2 result. I don't want to touch on that, the gravitational waves from the early universe, but of course that is very, very relevant to what we're talking about here. So if we move on to slide 6, I want to provide a very, very quick crash course in gravitational waves and general relativity. Now this will be very easy for some people, and basically I'm assuming no knowledge in GR, in general relativity. But the basic idea is that general relativity says that gravity is the curvature of four-dimensional space-time. Now there's a lot of implications to this, but the theory is sort of beautifully summarized by a quote from John Archibald Wheeler, where he said that matter tells space how to curve and space tells matter how to move. Okay, and this is summarized effectively in 10 partial differential equations, and these 10 differential equations are called the Einstein's field equations. They are written on the picture of the train on the left, and basically the idea, I don't want to go through any details about what this is, other than to say the left-hand side of this equation is pure geometry. Okay, so it's the geometry of the four-dimensional space-time. And the right-hand side of this equation, the T mu nu, is matter. Okay, so this equation is basically saying that matter is curving space-time, and the curvature of space-time is is being caused by matter, and it's also sort of telling matter how to move. So in this way, gravity is not actually really a force, but it's this effect of the curvature of space-time. So if you take this one step further, and I've got a picture in the top right on slide 7 of some ducks swimming along a pond, the basic idea is that any accelerating mass creates ripples in the fabric of space-time. Okay, and this can actually be stated more accurately as saying that they are propagating curvature perturbations. So if you think about the pond in this sort of very bad analogy, but we'll go with the analogy anyway. If you think about the pond being sort of the space-time, then as a duck swims along the top of the pond, it sends out little waves of energy, which are sort of the ripples in the surface of the pond. And these are, in our analogy with space-time, with the curved space-time, these are in fact gravitational waves. This is all very much formalized in Einstein's field equations, and so for a less hand-wavy derivation, I've got some bonus slides at the end that actually, if you click within the slideshow, within the PDF document, if you click on the bonus slides, it'll take you towards the end where I've got a slightly less hand-wavy derivation with some equations showing how gravitational waves come about, and I've also provided a nice reference to a paper by Flanagan and Scott Hughes, where they actually sort of do the full derivation of gravitational waves starting from scratch with general relativity. But most general relativity textbooks will have this in it. So the image to the bottom right is sort of one of the keys of gravitational waves here. This is a schematic of what happens when a gravitational wave passes through space. And so the way we think about this is that we think about test particles that move up and down and left and right. Okay, so if we move on to slide 8, there are two polarizations of gravitational waves. So just like in electromagnetism, there are polarizations of light. With gravitational waves, there are two polarizations of gravitational waves called the plus and the cross polarization. And if you just concentrate on the plus polarization, so on the top row of slide 8, you can see a ring of test particles here. And when the phase is 0, so initially this ring of test particles is just sitting as a circle. Now as a gravitational wave passes through, you can see an elongation in the y direction and a compression in the x direction. Okay, and then as the gravitational wave, that's sort of a pi on 2 phase evolution of the gravitational wave. As it goes another pi on 2 phase through the gravitational wave, the test particles return back to their original shape, and then it goes sort of in the other direction. So at 3 pi on 2, you've got an elongation in the horizontal direction and a compression in the y direction. So this really is the effect of what happens when a gravitational wave passes through. It really is the physical distance between any two bodies is actually changing. So in the below the line on slide 8, where I've got the word interferometer and sort of in brackets plus polarization. So what we're looking at here is essentially the same ring of test particles, but now overlaid on this ring of test particles is an interferometer. Okay, so the basic idea for an interferometer here is that you pass a laser a laser gets split into two beams. One of them travels vertically on the page, and the other travels horizontally. They go to the end. They bounce off a mirror at the end of their individual individual beam lines, and they come back, recombine. And if the distance if the distance of each of those arms is the same, then the light from the laser will recombine in such a way will interfere with itself, basically, is what I'm trying to say. And so then you can see that half a period later, when the y-axis has been elongated and the x-axis has been compressed, you can see that the gravitational wave has the effect that the interferometer, the light from the interferometer will combine in a different way. Okay, and so this is exactly how we plan to measure, or how we are trying to measure gravitational waves using interferometry. Okay, so of course, if you look at the slide, the picture on slide 8, you would say, well, this looks easy. As a gravitational wave passes through, it makes a very, very big difference. But in fact, that was obviously not to scale. And so if you move on to slide number 9 now, I've raised the question, why is doing this experiment, measuring a gravitational wave, really so hard? And the answer to that is gravity is really, really weak. So there are some detailed order of magnitude estimates in a really nice Living Reviews paper, Living Reviews in Relativity, by Satyaprakash and Bernard Schutz. But I just want to sort of summarize one of the basic arguments. We measure the size of a gravitational wave, or the amplitude of a gravitational wave, by its strain, and that strain is given the symbol h. So you can see this equation here, which is one of the very few equations that I have in this talk. So h is equal to the change in length, so delta L, so the change in length that you would see in the interferometer, divided by the actual arm length in your interferometer. Now, if we consider the merging of two black holes, for example, and two sort of stellar mass black holes located in a not too distant part of the universe, then what you can calculate is that this strain, delta L on L, should be around about 10 to the minus 22. Now, that's obviously a reasonably small number. So as a sort of thought experiment, let's consider building an interferometer with 1 kilometer arm length. Okay, now obviously you want to build this thing with as long an arm as you can, so you want L to be as big as possible so that you can measure this delta L. So if you have L of order 1 kilometer and a strain of 10 to the minus 22, then you find that delta L, or the change in arm length, is of order 10 to the minus 19 meters, or in other words, around about 1/10,000th the size of a proton. Okay, so this is ridiculous. These are ridiculous numbers. This is a ridiculously hard thing to do. So what I'm basically saying is you build an interferometer with 1 kilometer arm length, and you're looking for a change over that 1 kilometer of 1 part in 10 to the 22. Okay, so in other words, no wonder this is hard, and in fact, it's actually remarkable that we're anywhere near it. And we are. And what I want to show you over the next few slides is that we're incredibly close, and we're getting closer by the day, in a sense. So in terms of ground-based detectors, or in terms of actually building these interferometers, if you move on to slide 10, what you can see is a world map. And on that world map, there's a whole bunch of dots. So in North America, there are 2 detectors. They're called LIGO in Hanford, and there's a LIGO detector in Livingston. And at the bottom of the screen, there are some images of these. Now, these are 4 kilometer arm length detectors, so they spread out. So it's an interferometer where each arm spreads 4 kilometers. And these are the experiments that I'm a part of, and people here at University of Melbourne, and in fact across Australia, are a big part of. And there's a whole network of gravitational wave detectors around the world, and they're all sort of collaborating together. So the 2 LIGO detectors are the ones that are most developed, and I'll talk about exactly how developed they are in a second. The next most developed, and the one that has is working very, very closely with LIGO, is called Virgo, and this is located just outside of Pisa in Italy. And this is also a full-scale detector which should have very similar sensitivities to LIGO. In Germany, there's a detector called Geo 600. Now this has much shorter arm length, so the arm lengths here are just 600 meters. So this is more sensitive to high frequency gravitational waves, but it doesn't have as good a sensitivity as the LIGO instruments, but it is often used as a test facility for technology development and things along those lines. And there are two further planned detectors. So there's one called Kagra, which is located in Japan in the Kamiokande mine, which is where the neutrino detectors are. And they're already digging the tunnels for this one. So this is actually going to be, I think, 5-kilometer arms. It's going to have some fantastic new technology like some cryogenics, which will make the sensitivity extremely good. And the fact that it's underground also sort of suppresses various noise systems. And there's also one planned to be built in India, a LIGO India. But that's also a number of years down the track. So at the moment, we really have the two LIGO instruments and the Virgo instrument, which are the ones that are progressing extremely well. Okay, so if you move on to slide 11, this is sort of the start of the section. I really want to focus now on Advanced LIGO, and what I want everyone to take home from this is that gravitational waves will soon be a detectable reality. Okay, so in that sense, Advanced LIGO is making excellent progress towards achieving their sensitivity goals, and what I want to discuss is exactly what their sensitivity goals mean for detecting astrophysical phenomena. Okay, so if you move to slide 12, there's a curve, or there's a plot that I'm going to show quite a lot of. So what you have here on the horizontal axis is the frequency. So this is and on the vertical axis is the strain sensitivity. So this is basically how sensitive the instrument is to the gravitational wave strain at various frequencies. So you can see that there's a thick black curve, which sort of at a frequency of 10 to the 2 hertz is around about 10 to the minus 22 strain sensitivity. Okay, and so these are sort of the numbers that I was talking about before. Around about a strain sensitivity of 10 to the minus 22 is required to be able to detect anything. So what you can see on this plot is a whole bunch of colored curves, which are the actual sensitivity curves for the initial phase of LIGO. So initial LIGO did 6 science runs, and these were labeled S1 for Science Run 1, all the way through to S6 for Science Run 6. And Science Run 6 finished, I think, about a year and a half ago. And what you can see from this is that the 6th science run, or the 5th science run, I should say, was basically spot on the design sensitivity of where they wanted LIGO to be. Okay, so this is actually a remarkable feat in engineering and in prediction, that they sort of were able to predict where you would get the sensitivity in the gravitational wave strain. And the design of and implementation of the experiment actually got that sensitivity. And not only that, but in S6, that design was beaten. And so this was all done on schedule, on budget, and it was quite a remarkable experiment. So as I mentioned, the initial phase of LIGO ran, so the S6 science run ran sort of about a year and a half, 2 years ago, and then the detectors have been switched off. And they're being upgraded to a phase that's called Advanced LIGO. And the Advanced LIGO sensitivity curve, or the design goal for Advanced LIGO, is shown in the dotted curve at the bottom. So what you can see is it's about an order of magnitude better in strain sensitivity. It has different sort of frequency resolution. I don't want to concentrate too much on that. But that order of magnitude better improvement in sensitivity actually gets you a factor of 1,000 more sources. Okay, so it's basically a standard argument that the gravitational wave strain falls off like 1 on the distance. So if something falls off like 1 on the distance, you increase that distance reach by a factor of 10, then it means you see about 1,000 times more of the universe, okay, in terms of volume. Okay, so I guess the last thing I wanted to note on this slide is that LIGO is a consortium of 900 plus members, including 80 plus institutions across 17 countries. And I think Australia is about the 4th biggest contributor to that. So it's obviously the United States, it's Germany, it's the UK, and then I think Australia is the 4th biggest contributor to that. So we are actually a very large consortium here in Australia, and I'll talk about that in a little bit more detail shortly. But if you move on to slide 13, what I'm presenting here is an update of where the Advanced LIGO commissioning is at the moment. So there's a timeline on the bottom right of this plot, and you can see that the S6 data run finished around the middle of 2010. So I was a year off before, but anyway, finished around the middle of 2010, and that was the time when Advanced LIGO installation began. And so this is what's known as a dark period. So between 2010 and around about 2015, the instruments are being improved in many different aspects to get that order of magnitude extra sensitivity. Now, the plan is to have the first science data for the Advanced LIGO phase in 2015. So that's actually next year. So I think it'll be the third or fourth quarter of 2015, which is going to be amazing. So this is when, this is what I mean when I say that we are getting very, very ready for this. So what's sort of hot off the press, this is the June-July update. What you can see in the plot on the top left of this screen is the sensitivity curves during the commissioning phase of Advanced LIGO. So this is just for the Livingston detector. And what's really cool about this, it's a bit hard to see on this plot, but in purple, there is a sensitivity curve taken on the 30th of July, just this year. So what's that, a month and a half ago. And what this actually shows is it actually beat the initial LIGO sensitivity. So they've performed all of these hardware and technological upgrades. They've switched the detector back on, and already the sensitivity is, remarkable. It's improving on what was done previously. So, again, this is actually ahead of schedule. So this is ahead of schedule by about a month or two. The plan is always to do the Livingston detector first, and then they're going to do the Hanford detector next. And this is, this is phenomenal progress. It basically means that Advanced LIGO, without any big hitches, Advanced LIGO will start observing the sky on time in 2015. Okay, so of course you can follow LIGO on Facebook, and I've provided a link to LIGO's Facebook page there, and also to Advanced LIGO news site where you can sort of see some of these plots. But that's sort of a brief update of where everything is at the moment. So I haven't really talked about any astrophysics yet, you may have noticed, but if you move on to slide 14, I've got 4 separate boxes here which displays the 4 sort of classes of sources that we expect that we're looking for with the LIGO data. So as I'll explain shortly, the most promising source for gravitational waves are from coalescing compact binaries. So this is where you have binary neutron star systems, neutron star systems that in spiral together and actually merge. And it's that in-spiral merger that's going to produce an amazing amount of gravitational waves that should be detectable depending on the distance, and we'll get to that. So there's also neutron star and black hole systems and binary black hole systems that fall under this coalescing compact binaries. If you move down to the green box, there are a bunch of burst sources. These include core collapse supernova. So Advanced LIGO should be sensitive definitely if a supernova goes off within the galaxy, and also possibly within the local group. There's also things like pulsar glitches, magnetar flares, more exotic ideas like cosmic strings. There's a whole range of phenomena, of transient phenomena in the universe that Advanced LIGO may be able to detect that sort of come under this classification of bursts. Moving in an anti-clockwise direction, the yellow box there is a box that we work on in detail here at Melbourne University. So these are continuous wave sources, and the primary source here is rotating neutron stars. So the basic idea is that a neutron star that's rotating has some kind of asymmetry, and that asymmetry causes gravitational waves. And the advantage here is that you're not limited to looking for a gravitational wave signal that only lives in your detector for a matter of minutes or seconds, but the gravitational wave signal should be persistent for a long period of time, many years in fact. And so you can actually use that fact to integrate the signal over a very long period of time to try and get out the continuous wave signal and learn a hell of a lot about neutron stars and neutron star physics and fundamental astrophysics as well. So continuing to move along, the last box that I've got there in red is about stochastic backgrounds. So these are both astrophysical and cosmological. So this is really sort of where we start talking about relic gravitational waves from the Big Bang, in the same vein that BICEP 2 recently claimed detection of. There's also astrophysical sources like binary black hole mergers, but at larger distances and things like that. I don't want to talk too much about those in any detail during this talk, but if anyone has any questions, I'd be happy to sort of talk about it for as long as they want. So if we move to slide 15, I want to really focus on coalescing compact binaries, and in particular binary neutron star mergers. So, you know, the question comes up a lot, when is LIGO going to detect something? Now, I'm not going to give you an answer to that, but what I will point you to is a really nice review that was written in 2010 by the LIGO collaboration. And one thing that this does is it actually talks about the binary neutron star coalescence rate that you expect in the universe. And there are three ways in which you can get these in which you can estimate these rates. So the first is that we know about a lot of binary neutron star systems within our galaxy. Okay, so you can extrapolate on that, work out the number of binary neutron star systems that you expect in the universe, and from that you can work out an expected detection rate with in the gravitational wave detectors, so within LIGO in particular. Another way to do that is with things like population synthesis codes. Some of this work gets done by sort of Jared Hurley and collaborators at Swinburne. And of course, the other method, which isn't really discussed in the 2010 LIGO paper, but is through observations of short gamma ray bursts. So short gamma ray bursts are believed to be due to the merger of binary neutron stars, and so they're the sort of final death throes of a binary neutron star merger. So what I've got in the table on this slide is pulled directly out of that review from 2010, and the idea here is that the left-hand column is the epoch in which we're going to be doing the search. So 2015, the first row there is the first science run that's going to be done with Advanced LIGO next year. This run is going to, as you can see from the second column, this run is going to last approximately 3 months. And the third column, which is possibly one of the more interesting ones here, is the binary neutron star range in megaparsecs. So what this means is that that 2015 run, if Advanced LIGO hits its design sensitivity, then it will be able to detect binary neutron stars out to about 40 to 80 megaparsecs. Okay, so when you then fold that number into these estimates for the rates, what you find is that the number of binary neutron star detections is somewhere between 0.0004 in that 3-month period and 3 detections. Okay, so if we're incredibly lucky, and we would have to be incredibly lucky, as you can tell from those estimates of the number of binary neutron star detections, then you could actually see up to 3 binary neutron stars go off in that first phase of Advanced LIGO. So I'll let you peruse that table at your own leisure, but just to sort of note that by the time you get down to around about 2019, the LIGO detectors are going to be on basically full time. The binary neutron star range is around about 200 megaparsecs, and this actually means that even in the most pessimistic case, you will see around about 0.2 detection. You'll get about 0.2 detections per year. Okay, so if you just take sort of the mid-range of that, you expect to see many of these detections per year. Okay, and let's remember that 2019 is only around about 5 years away. So, you know, it's anyone's guess as to whether the first detection is going to come in sort of 2016 or whether it's going to come in 2020 or 2021. But you'd be hard pressed to say that it will come much after that. So one thing that's missing from this table is the Japanese detector KAGRA. What you can tell from the bottom row of this table is when you include the LIGO India detector, the rates increase by a factor of 2. If you include the Japanese detector in that, you get another increase in the rates again. And so this is sort of, you know, all of this information is making detection, I guess, a reality in sort of the near future. So if we move on to slide 16, then you'll notice that the table is now gone and it's replaced with some plots of the globe. So what I'm showing here is the localization accuracy. So this is from a different paper, a different LIGO paper, just from last year. And this is showing the localization accuracy with a network of detectors. Okay, so in the left-hand plot, what you can see is the typical error bars on localization of a binary neutron star system if you have the 2 LIGOs and a Virgo detector. And what you can see on the right-hand plot is that this sensitivity gets much, much better when you add the Indian detector in there. Okay. Now, I won't go into the details of why this is, but other than to say that you need to triangulate between your sources, between your detectors, to get the source location. So adding in a LIGO in India, which is sort of a little bit off the plane of the other detectors, makes a significant difference as to where you expect to detect gravitational wave, the source localization that you expect. Okay, and just the other thing to say is that there's I mentioned earlier the follow-up work with the electromagnetic telescopes and actually sort of searching for these things with LIGO triggers. There's been a whole bunch of studies on detection efficiencies of electromagnetic counterparts to these gravitational wave signals. And the odds are reasonably good. I mean, it depends a lot on the beaming fraction of short gamma ray bursts and things along those lines. But you expect to see a reasonable proportion, sort of anywhere from some 1 in 5 to 1 in 10 of binary neutron star mergers you expect to see also in electromagnetic counterparts. Okay, so if we move on to slide 17, very, very briefly, we know a lot less about neutron star black hole mergers than we do about neutron star mergers. You can get estimates on the rates from population synthesis codes and also from short gamma ray burst observations to some extent, although I think there is some debate about that. But just by way of an example, there was a recent paper from a Japanese group from Yonatoku et al. Where they actually predicted around about, well, you can see the number there, 146 plus or minus about 75 neutron star black hole mergers per year with an array of detectors. And so that again is, in 5 years' time, type of timescale, then you expect to be detecting one every couple of days. But that is, I would argue that the uncertainty on that should be even higher, but that's a discussion for another day. And then finally, there's black hole mergers, and of course we know very, very little about the rates of these, and so I won't really say anything further. Other than to say, you switch LIGO on, LIGO is going to be the way that you learn about these black hole merger rates, and that you get some kind of constraints on them. Okay, so if we move on to slide 18, I'm trying to put this all together and put this into a little bit more context. So what you can see on slide 18 is this is again the strain sensitivity as a function of frequency, but now you can see that I'm going over about 15 orders of magnitude in frequency. So the black curves to the right are the LIGO frequencies or LIGO sensitivities. And the reason I'm showing this plot now is that I'm actually going to go, very soon I'm going to start talking about the pulsar timing arrays. And you can see that the pulsar timing arrays are sensitive to a very, very different frequency band and therefore very, very different sources. So if we move on to slide 19, just very quickly, I've put on where you expect the neutron star, and the binary black hole mergers to occur in this parameter space. Okay, slide 20, I'm again going back to a previous slide that I showed just to reiterate that there are a whole bunch of different types of sources that you expect to be detectable with LIGO. So again, there's the coalescent compact binaries that we've just talked about. There are burst sources, continuous wave, and also stochastic backgrounds. And the reason I bring that up is that if you go back to slide 21, what I've tried to do is I've tried to put some of these sources or estimates for these sources on the plot. So on slide 21, you can see a big green box, which is core collapse supernova. Basically, the modeling for this is very hard. It's hard to work out how loud gravitational waves you should be, and so there's therefore a large uncertainty. Other than to say, we didn't detect supernova with initial LIGO, but then again, it's not clear that a core collapse supernova actually went off in the galaxy during that time. So other things I've got there are upper limits that we've put on the Vela and Crab pulsars, just from sort of the elliptical nature of those pulsars. If there's some kind of asymmetry, then you would expect gravitational wave emission. And the other couple of sources I've put on there show a little bit of bias. There's SCOX1, which is a low-mass X-ray binary, which again you expect to emit gravitational waves. I say there's bias there because we're working on that here at Melbourne University. And the other one I've put on is magnetar flares, and that's definitely biased because those limits are actually my predictions. But anyway, we'll move on. So if you go to slide 22, I want to just quickly say that Australia is actually making very, very big contributions to Advanced LIGO. So within Australia, we have this thing called the Australian Consortium for Interferometric Gravitational Astronomy, or AKIGA. It's probably not the best acronym in the world, but it's not too bad. We are 50+ members, over 7 institutions, and we're doing lots of cool science. And I want to very briefly tell you about some of that cool science. So just to say that we are made up of Melbourne University, Monash University, UWA, University of Adelaide, the ANU, also Charles Sturt University, and CSIRO Precision Optics. So LIGO science in Australia, if you move to slide 23, we're doing a whole bunch of stuff associated with gravitational wave data analysis. This includes real-time triggers for electromagnetic follow-up observations, and this is primarily being done in UWA. We're doing gravitational waves from supernova remnants, so that happens in Melbourne University and also at ANU, and we're searching for things like the supernova remnant in Cassiopeia A, and I also presented last week the supernova remnant search for 1987A at the Supernova 1987A conference in Coffs Harbour, the Castro conference. We're also doing searches for low-mass X-ray binaries, in particular what we expect to be the loudest, Scorpius X1. And moving down this list, you can see, moving into the blue, there's a lot of astronomy and astrophysics going on that is very closely related with LIGO. So these include X-ray and optical observations that are being led sort of by Duncan Galloway at Monash University, giving precision ephemerides for LMXBs. And so this feeds directly into the gravitational wave searches and restricts the parameter space over which you need to search. As I mentioned earlier, there's a lot of multi-messenger follow-up with memoranda of understanding being signed between a lot of observatories and LIGO. And there's also a lot of source predictions and astrophysics being done. So that includes things like neutron star physics, calculations of stochastic backgrounds, Corcular supernova, and I'm sure I've missed out on a few there. So that's just in terms of astronomy and astrophysics. If you move on to slide 24, I've tried to summarize a little bit about what the experimental community is doing, and there is actually a very large contribution here. So the first item there is quantum squeezing, and I'll go into that in a bit more detail in a second. In Australia, we're also building and designing mirror suspension systems for the interferometer, arm-length stabilizations, which help the entire interferometer sort of lock into a stable state. Wavefront sensors, as I'm sure some of you will know, there is a high optical power test facility an hour outside of Western Australia, and if you go to next year's ASA, then I think you might go for a tour of that facility. We do things like low loss mirror coatings, investigations of instabilities within the interferometer themselves, and of course commissioning personnel. So people from Australia actually get sent over to the LIGO detectors to implement some of the experimental apparatus that have been built. So if you move on to slide 25, I just want to spend two very brief minutes talking about something that was done primarily driven by at the ANU in Canberra, and this is quantum squeezing as beating the quantum limit. And this was published by the entire LIGO collaboration in Nature Photonics last year, but as I mentioned, this was sort of driven by by researchers at ANU. So the basic idea here is that the light that you can do this thing called optical squeezing of the laser light that goes into your interferometer, and the idea is that you're trying to beat the Heisenberg uncertainty principle, and sort of the photon number and phase are a Heisenberg uncertainty pair. And so if you basically dump all of your uncertainty into one of these, into the photon number, then it means you can get remarkable accuracy on the actual phase. And of course, if you know the phase of the light, this is exactly what you want to use to measure the gravitational wave signal. Okay, so this is sort of the very basic premise of how LIGO works. There's a little link where it says Nature there to the Nature article, which also comes along with a sort of a more popular explanation. But this is just to point out that this is technology that has already been proven within LIGO. but is not factored in when you talk about the initial sensitivity curves, and it has the potential to improve sensitivities by a factor of around about 2, maybe a little bit less. But of course, the sensitivity increase of a factor of 2 again increases the volume over which you're searching by around about a factor of 8. Okay, and so this has the potential to increase those estimates that I was talking about before quite significantly. Okay, so if you move on to slide 26, this is just sort of the take-home messages for Advanced LIGO. Again, my take-home message is that gravitational waves will soon be a detectable reality, but in more detail, Advanced LIGO is going to start observing next year, all things being equal. The best sources are compact binary coalescence, but this is going to have a major influence on multiple subfields of astronomy, and I haven't gone into that in all that much detail, but there is some physics and astrophysics that can be done with gravitational waves that really can't be done with anything else, with any other kind of technology, with traditional telescopes. And the final note there is that Australia is playing a very, very significant role in all of this. Okay, so if we move on to slide 27, I'm going to change gear a little bit, still talking about gravitational waves, but talking in particular now about pulsar timing arrays. And what I want to focus on here is that the key concept, again, is that precision pulsar observations can detect cosmological gravitational waves. So now, instead of talking about reasonably local events, our binary neutron star mergers needed to happen within a few hundred megaparsecs, we're now talking about supermassive black holes around about, well, at sort of redshifts of 2 and things along those lines. So if you move on to slide 28, these are some cute slide that I sort of borrowed from Vikram Ravi. In the top left, you can see one of the Smurfs is trying to measure the distances in a classic sort of interferometer way, in the way that we were just talking about with LIGO. So he has his test masses, 2 test masses, and sends off laser beams orthogonal to each other. The way a pulsar timing array works is more with the image on the top right, where there are a whole bunch of test masses, and you want to measure, in a sense, the distance to each of those test masses in a bunch of different directions. And this is done using precision timing of millisecond pulsars. And so then what you're basically doing is you're looking for a correlation between the change in distance between each of those test masses. So this is illustrated in the bottom right with one of the sort of typical pictures that's shown in most pulsar timing array talks, where you've got the Earth as in the center, you've got lots of pulsars located all around the place, and you're measuring the distance to each of those pulsars as a gravitational wave is passing through. Okay, so millisecond pulsars have incredibly stable spin periods, whereby a lot of work has been done on this in Australia by the Parkes Pulsar Timing Array group, but the timing of these millisecond pulsars rivals the best clocks on Earth. And so if we move on to slide 29, just to point out that there are 3 international groups working on pulsar timing arrays and trying to detect gravitational waves using pulsar timing. The first is obviously the Australian one, Parkes Pulsar Timing Array, which uses the Parkes telescope in New South Wales. There is a group in Europe, the European Pulsar Timing Array, and there's another one called NanoGrav, which is the North American consortium. Now, what I've neglected to put on this slide is that there's actually an international pulsar timing array, which is looking to combine all 3 data sets to create sort of an almighty, all-conquering data set. And that's something that's sort of in the pipelines at the moment and is reasonably well developed. But if we move on to slide 30, we're going back to this slide to this image I showed before, where we have a plot again of the strain sensitivity as a function of the frequency. But now what I've put on is the sources that you expect in pulsar timing arrays. So as mentioned, the main source is from supermassive black hole binaries, and the merger is of supermassive black hole binaries, and a lot of work is being done throughout Australia and sort of particularly at Melbourne University, and I better say this because Vikram Ravi is sitting next to me, but he's sort of driven a lot of this work with his collaborators, but trying to provide the predictions of where you expect supermassive black hole binaries to sit on this plot. So schematically, it's there in the red shaded region, but there are a lot more sort of precision estimates of where this space should be. Other things that you might expect within this band, cosmic strings, and also the Big Bang relics, where Big Bang relics are again things like inflation or relics from inflation that BICEP 2 claim to measure. So if you move on to slide 31, astrophysics with the Parkes Pulsar Timing Array. Ryan Shannon, Vikram Ravi, and the rest of the Parkes Pulsar Timing Array published a paper in Science just last year, which was entitled "Gravitational Wave Limits from Pulsar Timing Constrain Supermassive Black Hole Evolution." So what you can see, or I guess the take-home message from this, is that the gravitational waves are actually, or the gravitational wave science is actually doing astrophysics with the pulsar timing arrays. So they've constrained galaxy evolution models, and in particular supermassive black hole evolution, using upper limits of the gravitational wave signal. So again, it's using non-detections of gravitational waves. And I've sort of quoted here from the abstract, using observations from Parkes Pulsar Timing Array, we constrain the fractional gravitational wave background energy density to be approximately a factor of 6 more stringent than previous limits. Okay, so this was a significant improvement over the last limits. And then the next sentence there is, we compare our limit to models of the supermassive black hole population and find inconsistencies at confidence levels between 46 and 91%. So, you know, this is actual astrophysics being done in Australia with gravitational waves. And there's actually a link, hopefully, to a very cool video that was sort of produced at Swinburne there, and is on YouTube, and you can go ahead and find it. It's entertaining to watch and narrated by Vikram as well. So if you move on to slide 32, just my take-home message for pulsar timing arrays, and again, I just want to reiterate that precision pulsar observations can detect cosmological gravitational waves. It's anyone's guess as to when a positive detection will happen, but even in lieu of a positive detection of gravitational waves, astrophysics is being done with gravitational waves now. And you know, the further note to that is the Australian consortium is really leading the world in this field. So if we move on to slide 33, I've got my conclusions there, and I've limited them to be sort of some snappy punchlines. The first one, just to say that the first direct detection of gravitational waves is imminent, and the next one to say that they will provide a new and truly exciting window on the universe that will be opened up. And once we start looking, we will never stop, and there'll be some amazing sources and amazing discoveries in this space in the next few years. And I'll leave it there, other than to say there are a whole bunch more slides after this, including some slides on LISA, and including some short mathematical derivations of gravitational waves and things like that. But I'll leave the main body of the talk as is, and say thank you very much. I think you might be on mute, Darren.
Can you hear me now?
That's better.
Yeah, sorry guys. Discovering the joys of the mute button. So just wanted to say thank you very much to Paul, once again, this time out loud, and to let you know that this lecture will be up online in a few hours' time. If you want to watch it again, or if you want to recommend it to someone else to watch. And I encourage you to share it with your students and others. There's a whole host now of ANITA lectures covering a range of topics, and we'll be continuing to add to those as the months and years go past, and you can find them on the ANITA webpage. So let me say again, thanks to Paul. If you have any more questions, hopefully you'll be sticking around for a while, and you can put them in the Google Plus comment bar, and he'll come in and try and see if he can give you an answer to that. Hope you have a great day, and thanks again for watching. Bye.